Okay, so now we're back, and now we're in section 10.2. So now we're going to be looking at the difference of means, and we're going to be looking at intervals and tests. And the first thing we're going to start with is the sampling distributions that we're going to be looking at. So suppose we want to compare the means of some quantitative variable for individuals in population 1 and population 2. The ideal strategy is to take a separate random sample from each population and compare the sample means x bar 1 and x bar 2. We compare the populations by doing inference about the difference of mu1 minus mu2. So again, reinstating that this is what we're going to infer about the populations by using our sample data. And the statistic that estimates this difference is x bar 1 minus x bar 2. So again, looking at our sample data. So we know these about the individual distributions, x1 bar and x2 bar. We know quite a bit, but what happens when we combine them into one distribution? Well, we know that if our population distribution is normal, so is the sampling distribution. But we also know that if the population distribution is not normal, but each sample, both of them, are large, meaning greater than or equal to 30, then our sampling distribution will be approximately normal. We know the center of that distribution will be centered at our mu1 minus mu2. And then our spread can be combined by combining those variances. So the standard deviation of 1 squared, so this is how we get standard deviation squared over, and the square cancels out with the square root over n. So the standard deviation of 1, and then I have that same thing for the other, so that really we're just adding these variances together, and then we square root to calculate standard deviation. And again, we have to have that, we can only use that if we know that we meet that independence condition. So a potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Camberley Inc. The weights of potatoes from Riderwood Farms are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. Now the weights of potatoes from Camberley are approximately normally distributed with a mean of 180 grams and a standard deviation of 30 grams. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and weigh them. They are surprised when the average weight of the potatoes in the sample from Riderwood Farms was higher than the average weight of potatoes from the sample from Camberley Inc. So let's look at the sample, the shape, the center, and the spread of the sampling distribution of XC minus XR. So we're looking at Camberley minus Riderwood. And so the shape should be approximately normal, because both of the original distributions were approximately normal. So when we combine it, it should still be approximately normal. Now, our center of XC minus XR should be the mean of C. So our mean of C was Camberley, 180, minus the mean of R, 75. So we'd expect the mean of this to be 180 minus 75, which should be 105. And then our spread should be us combining those two standard deviations. So the square root of our standard deviation squared, let's see, 30 squared divided by our sample size, 20, plus our standard deviation squared, 25, squared over our sample size, 20. So now we're going to go ahead and we're going to check, let's see, 30 squared divided by 20 plus 25 squared divided by 20. which gives us 76.25. Let me just calculate that one more time. Yep, looks good. And then I square root that answer. And I get a standard deviation of 8.7321. Okay, so now we're going to go ahead and look at the actual problem. Find the probability that the mean weight of Riderwood sample is larger than the mean weight of Camberley sample. So when I take the mean of Camberley and I subtract the mean of Riderwood, we're thinking, let's see, the mean weight of Riderwood, so XR is going to be greater than Camberley. So I'm kind of looking at it like, how can I change this into this? And so the first thing I'd want to do is flip this bottom one around. So now it's XC is less than XR. And then I would subtract this from both sides. So now I get XC minus XR should be less than 0. So that's what we're looking for. We're looking to see that the difference is less than 0. And so a lot of times we have to sit there and manage our way through that to be able to figure out how am I checking this out. So let's look, how does that distribution look? Well, we're centered at 105. Oh, that's 175. No wonder that seems so weird. This is 175. So this is just 5. So we're centered at 5. Much better. And then we have a standard deviation of 8.7. So 5 plus 8.7 gives me 13.7 right here. 5 minus 8.7 gives me negative 3.7. So when you kind of look at that and you think, well, hey, 0's right here, there's not that, I mean, that seems like a pretty high probability. Well, let's go ahead and calculate that then. So let's say it's a normal distribution, so normal CDF. We're going to have our lower bound to be really low, so somewhere on here, let's just say negative 100. Our upper bound should be that 0, because we want to know the probability that it's less than 0, right? Because that's what we calculated. And our mean we figured out was 5, and our standard deviation we figured was 8.7321. And we can go ahead and calculate that probability with a little bit more exactness than we would be able to do just by looking at this ugly picture. But it helps us figure out what's going on. So negative 100, 0, 5, 8.7321. And we get a probability of 0.2835. Should they be surprised? No. There's a 28% chance that Camberley would have a higher sample. Oh, Camberley would have a lower sample. Helps if I read better. Okay, and so that's really what we're kind of working with. So now we're going to start looking at that sample T statistic. If we start with the Z statistic, we can modify to replace standard deviation, which is our lowercase sigma, from the samples. And so then we can start using our standard deviation of our sample in there. So we're going to put that in there, which now gives us our standard error. And so now by doing that, we're starting to look at those T distributions. So now we can standardize our T values. So we get our samples minused on top. We get our standard deviation formula. And this is our two-sample T statistic that we're going to be working with. And the two-sample T statistic has approximately T distribution. But really important to know, it does not exactly have a t-distribution, even if both populations are both exactly normal. But our approximation is going to be really accurate, and it's going to be close enough, so we're not really going to worry about it. So now with every t-procedure, when we start calculating our t-CDFs, we always have to look at degrees of freedom. So we have two different ways of doing this, and we have technology. So when you plug everything into your calculator and let the calculator do your tests for you, it uses this really complicated degrees of freedom formula. In fact, I have it right down here, so it's easier to read. And so it uses that standard deviation, or that standard error formula. And then it uses this 1 over n minus 1, and then it uses the standard error and over 1, n minus 1, and you almost always get decimals because of that fraction thing that goes on. And so if you're using your calculator to be able to do this, if you're using this formula, use your calculator to do it for you. Just use the built-in tests and stuff like that. Don't ever try to calculate this by hand or with your calculator by plugging and chugging. It's just way too crazy. But because of this formula, we have to be really careful. Our sample sizes always have to be 5 or greater. You can never have a sample size less than 5 for this stuff to work. So your samples need to be bigger. But what we typically do is we play conservative, which means we may have a higher probability, but it's kind of playing the safety game. And so now what we're going to do is we're going to use the smaller of our two options. So the sample size of the first sample, minus 1, or the sample size of the second sample, minus 1. Whichever one ends up smaller, that's going to be our degrees of freedom. And that's okay, because that's going to be, it's going to give us a little bit of room to play with, and it's going to help us keep safe. So again, this is really more accurate, but this is okay. This is good enough for what we're doing. If we were doing medical stuff, we'd be using technology that would calculate that out for us really nicely. But keep in mind, as long as the bigger our sample sizes are, the more accurate our answers are going to be. So we'll be fine. And that's it for today. So next we're going to start actually looking at those confidence intervals.